Good morning to everyone. I am Dr. Sumi MS. The name of the course is Electromagnetic Fields and today's lecture topic is plane waves in lossy medium. On completion, the students will be able to define what a lossy dielectric medium is and also understand the propagation of wave in lossy dielectrics. Wave propagation in lossy dielectrics. A lossy dielectric can be described as a medium where some fraction of the electromagnetic wave power is lost as the wave is propagating through the medium. This power loss is mainly due to poor conduction. Attenuation constant alpha is the measure of the spatial rate of decay of the electromagnetic wave in the medium, which is measured in nepers per meter or in decibel per meter, and this attenuation constant is equal to 0 in the case of a lossless dielectric, whereas in lossy dielectric attenuation constant has a value. Phase constant beta is the measure of the phase shift per length and is called as the phase constant or wave number. The diagram represents an electromagnetic wave which is being propagated in a direction perpendicular to both the electric and magnetic fields. So here the three axes are mutually perpendicular to each other. None of the dielectrics available today are generally lossless. Every dielectric offers some kind of loss to the electromagnetic wave propagation that is propagating through it. The wave propagation in a lossy dielectric can be considered the general case of a wave propagation. Let's consider electromagnetic wave propagation in a lossy dielectric. Explaining wave propagation in lossy dielectric. A lossy dielectric can be described as a medium where some fraction of the electromagnetic wave power is lost as the wave is propagating through the dielectric. This power loss is due to poor conduction. A lossy dielectric offers a partially conducting medium with conductivity sigma which is not equal to 0, and the lossy dielectric can be represented with the parameters conductivity, permeability and permittivity as follows. Conductivity is not equal to 0 and permeability is equal, mu is equal to the product of mu r mu naught, where mu r is the relative permeability of the medium and mu naught is the permeability of free space, and permittivity epsilon is given as the product of epsilon or epsilon naught, where epsilon r is the relative permittivity of the dielectric and epsilon r is the permittivity of free space. Maxwell's equations governing a linear isotropic homogeneous charge free lossy dielectric can be obtained as in the given four equations. By taking curl on both sides of the equations 3 and 4, we can obtain the Helmholtz equations which are mentioned in equation 5 and 6 respectively. Considering the propagation constant gamma, which is given as alpha plus j beta, where alpha is the attenuation constant and beta is phase constant as in equation 7, and alpha and beta can be written as mentioned in equation 8 and 9 for the dielectric material. With these considerations, if we assume that an electromagnetic wave is propagating along the positive z direction, that is with along az in a dielectric, and Es is the electric field that has x component, we can represent the value of electric field as in equation 10. Substituting equation 10 in the equation 5 Helmholtz equation, we can get the scalar wave equation as given in equation 11, and according to the assumption that the electric field must be finite, we can consider the second part of the equation 11, E naught dash equal to 0. Therefore, this equation 11 can be simplified as mentioned in equation 12, and here the magnitude of the electric field versus time can be plotted. Only the x component of the electric field travels along the positive z direction. Similarly, the same principle can be used in obtaining the magnetic field also. And here the equation for magnetic field along z direction with respect to the wave propagation is given as in equation 13, and equation 14 we have the relation between E naught and H naught, given as H naught is equal to E naught by eta, where eta is the intrinsic impedance of the medium, which is given in equation 15. Substituting the values of equation 14 and 15 in equation 13, we can get the magnetic field as represented in the below equation. Attenuation constant, phase constant, and loss tangent. From equation 16, we can conclude that as the wave propagates through a lossy dielectric along the z direction, the amplitude is attenuated by a factor e power minus alpha z, where alpha is the attenuation constant of the medium. And this attenuation constant is a measure of the spatial rate of decay of the electromagnetic wave in the medium, measured in nepers per meter or decibels per meter. Phase constant beta is the measure of the phase shift per length, and from equations 12 and 16 we can tell that at any instance of time the electric and magnetic fields are out of phase by a phase angle theta n due to complex intrinsic impedance of the wave of the medium, and the electric field leads the magnetic field by a phase angle of theta n. In a lossy dielectric medium, the ratio of the conduction current density to that of the displacement current density is expressed in the equation 17, which results in a value tan theta, which is called as the loss tangent, which is given as tan theta is the ratio between conductivity to angular velocity times the permittivity of the medium. Wave propagation in the lossy dielectric is a generalized approach to understand the propagation through other types of mediums. Quiz questions on plane waves in lossy dielectric. What do you mean by a lossy dielectric medium? Describe the propagation of wave in lossy dielectric medium. Thank you.